The second property that we want to confirm is that the diagonals will bisect the vertex angles of all rhombuses. So if we have a rhombus, the diagonals will have to bisect the vertex angles. Now the word vertex is talking about the angles here at A, B, C, and D. These are called the vertices of our rhombus, and these vertex angles at A, B, and C are going to be bisected by each diagonal that's drawn. So if it's bisected, that means this entire angle here has to be cut into two equal parts here and here. Bisect in by the base word means to cut into two equal parts. So we're going to show that the angles have to be cut into two equal parts. And this is where we're going to be able to piggyback off of what we did last time. We know that ABCD is a rhombus, and that's what we're given. And because it's given to us as a rhombus, we know that all four of these sides are equal length. So my master plan on this one is to show you that all four of those triangles are identical. Not only are the top two that we did earlier congruent to each other, but these two are also congruent to the bottom two down here. And all four triangles are congruent. So really what you have is, in a rhombus, anytime you draw the two diagonals, you create four congruent triangles. And those congruent triangles then will help us show that these corresponding parts are the same, and these corresponding parts are the same. So if those are the same size because the corresponding parts are triangles, then this angle had to be cut in half because they're equal in measure on each side. So that's kind of the outline of it. And I erased my ABCD rhombus given. So what we can do is we can outline our proof this way. All these sides are equal in length, so we know that AD is congruent to BC, or DC, which is congruent to CB, which is congruent to AB. I just worked around counterclockwise from A, and that is, by definition of a rhombus, that all sides of a rhombus are congruent. Some people maybe would put the definition of a rhombus. That wouldn't be too far off. It's one of the acceptable definitions of a rhombus. It's a parallelogram with four congruent sides. So we have that, and then from the idea that these were, it's a parallelogram, we now know that the diagonals bisect each other. So I'm going to write both of these. The two tick marks from A to E has to be congruent to C to E. And the triple tick marked ones, DE, has to be congruent to BE, because really what those are those are diagonals, and anytime we have a parallelogram, the diagonals of a parallelogram bisect each other. So we know those two parts have to be congruent. So if you look at that and look at all four of these triangles, they all have the same tick marks. One on the outsides, two on the inside, and a three. So I'm looking at, let me get a highlighter here so I can keep track of it better myself. So that I know that this triangle here matches identically with the triangle down here because it has a one tick mark, a double tick mark here, and a triple tick mark up on this side. Well, that's the same tick marks or markings that you have on this triangle. This triangle is got to be congruent to the triangle to the left or up here by the same reasons, because we have the same tick marks, 1, 2, 3, and 1, 2, 3, and then we can come back to the last one here. So hopefully I am showing to you that all four of those triangles have to be congruent, and I've convinced you of that. So I'm going to get rid of all that shading. So if those are congruent triangles, so I can name triangle A, D, E, or maybe I'm going to go with E in the middle every time because that'll make it a little bit simpler. So, whoop, that's not going to work very well. Let me try that again. See if it's going to write in pen. Okay, let's get a pen. So triangle AED is congruent to triangle, working around clockwise, it's going to be CED, which is congruent to, now I'm going to kind of wrap around down here. We work around this one, it's going to be CEB, sure I got that. D. Probably could go B, E, C, which is congruent to the last triangle here. And that is A, E, B. Now these triangles are all congruent for the exact same reason, because we have proven that they are congruent by the side, side, side congruency theorem. Now what's important about that is that we can now identify their corresponding parts. This angle here corresponds to this angle here in the triangle. And it also corresponds to the angles over here and here. Those angles, whatever we're going to call them, 1, 2, 3, 4, angles 1, 2, 3, 4, have to be congruent by C, P, C, T, C. So because they're all congruent, that means that that diagonal had to bisect them. So because angle 1, angle 2, and angle 3, angle 4 are all congruent to each other, that meant that the diagonal AC bisects angles A and angle C. Cut them into two equal parts, so by definition of an angle bisector. And now we can do the same analogy on the other ones. We're going to look at angles 5, 6, 7, and 8. Again, these all are equal to each other because of CP, So we know that angle 7 is equal to angle 8, which is equal to angle 5, which is equal to angle 6 by CP, But because we've established and shown that angle 7 and angle 8 are the same, that angle D had to be cut in half. So angle D, I'm going to write it the same way I did before. That means, oh shoot, I lost that. Angle 7, congruent to angle 8. And now I'm going to use the diagonal BD, had to bisect angles D and angle B by definition of an angle bisector. So what we presented is the fact that we now know that every time we draw the diagonals of a rhombus, they will bisect those vertex angles.